you very much, Charlotte. Good afternoon, everyone. Welcome from my side. I would like to thank the examiners, the audience in this room, and those online for joining me today. Now I'm going to walk you through some highlights of my PhD research in the past 3 years. Okay, good start. Yeah, it works. So to warm up ourselves, I want to talk about what is atmospheric turbulence. Atmospheric turbulence refers to the random fluctuation of the wind. Imagine ourselves walking outside in an open field, maybe on a sunny, warm day, and the wind is just breezes. But suddenly, the weather changes, and you can see some clouds accumulating over the sky, and you feel the temperature drops, and the winds get stronger. If you are now walking towards or against the wind, you will feel that the wind is pushing you backwards. You feel the wind forces on your body. Or if you are passing by some houses or trees, you can also feel that the wind velocity and speed is changing all the time. That's because the wind meets the obstacles on the ground and is slowed down. Being a wind turbine standing in an open field, it also feels those fluctuations of the wind all the time and reflects the impact of atmospheric turbulence on its power output and structure load. Therefore, if we want to effectively harvest the wind power and protect the wind turbine from fatigue damage, we need to characterize and understand the atmospheric turbulence of the wind turbine inflow. In the wind energy context, why is turbulence important for wind energy? I would say turbulence is important for different applications. Before we deploy a wind turbine at the site, we need to first assess the site conditions, if the wind condition is suitable. And second, if we want to build up the wind turbine in the wind turbine design phase, we need accurate turbulence information to define a good power curve, and also to calculate how much material we need to construct the wind turbine. Since many wind turbines are operating inside a wind farm, turbulence information are valuable to study the interactions between the interactions of the flow between wind turbines, and then effectively control the wind turbine to optimize the power output and reduce the structural load to extend the turbine's lifetime. So turbulence is important, and how can we measure atmospheric turbulence? Traditionally, turbulence is measured by the anemometers. Is mounted on the tall meteorological mast. Usually there are some fuses, and you can mount them on fuses. For example, here I'm showing a picture of a sonic anemometer, which can provide three-dimensional turbulence parameters, and it is used in the international standard. However, with the increasing size of modern wind turbines, it is more and more expensive and infeasible to build up and maintain this tall net mass, especially in the offshore conditions, since large foundations are needed to really support the mass. Also, the net mass is vulnerable to high wind. They can be blown down. And our LiDAR, which represents the light detection of and ranging, is a cost-effective alternative to the tall net mass. Depending on the application, the LiDAR can be deployed on the ground and measure the wind upward, shooting laser beam to the sky, and measure the wind at different heights. It can also be put on a buoy to become a floating system to assess the offshore conditions. And lastly, this picture shows a LiDAR mounted on the top of the turbine, which is called the nacelle-lidar. It can be used in the forward-looking mode and always track the wind turbine inflow. My PhD project focuses on the forward-looking nacelle-lidars. Compared to the anemometers installed on the net mast, the nacelle-lidar, forward-looking nacelle-lidar, can scan the inflow with very high spatial resolution. Here on the right side, I'm showing an animation of the spinner LiDAR. It measures the inflow with a Rosetton pattern, as you can see this black curve. The spinner LiDAR is first designed to be installed in the spinner and thus got its name, but it can also be used on the top of the turbine. Here, the color shows the radial velocity measurements from the spinner LiDAR. Another advantage of forward-looking nacelle LiDAR is that I mentioned it in the last slide, that it can yaw with the wind turbine and always track the inflow. Also, as a remote sensing device, the nacelle LiDAR can measure the wind before it hits the rotor, so it provides a wind preview, which is very valuable for wind turbine control. We will see this multi-beam LiDAR a lot in the next few slides, so I want to give a little bit more information about it. The spinner LiDAR is based on a continuous wave system, and as you can see, it can scan the inflow at 400 radial velocities at 200 Hertz. So it's really give us a really detailed information of the inflow. It completes the scan every 2 seconds. The half cone opening angle, which means the angle between the center line of the scanning pattern and the beam, is between 0 degrees to 30 degrees for the spinner LiDAR. So I want to introduce a bit how the LiDAR measures the wind, if the audience is not familiar with that. So just like SODAS or radars, the Doppler LiDAR measures the wind using Doppler effect. The coherent Doppler LiDAR emits coherent laser beam into the atmosphere. The aerosols that is traveling with the wind will be illuminated. And if the aerosols is traveling towards the LiDAR, according to Doppler effect, we will have an increased frequency in the backscatter light. Therefore, the radial velocity of the aerosols is proportional to the laser wavelength and the difference between the backscattered frequency and the emitted laser frequency. However, the LiDAR measures the wind not only at its focus point. It measures the velocity within the range around the focus point, which is called the probe length. And since the LiDAR beam has a cylinder form, we also usually refer to the probe volume. So the velocity detected exactly at the focus point will weight the most, and the further away is measured from the focus point, the less it weighs. All these informations are collected and saved in the so-called LiDAR Doppler spectrum, which shows the distribution of the weighted velocity within the probe volume. Here I'm showing a curve, a plot of the simulated Doppler spectrum. On the horizontal axis, you can see the radial velocity gains, and on the vertical axis is the signal strength. This can be seen as a histogram of the weighted velocity in the probe volume. A dominant radial velocity will be determined from the Doppler spectrum and be streamed out from the LiDAR system, and that is the measurement we got from the LiDAR system. So now we might ask ourselves, can LiDAR measure turbulence? Turbulence is usually be calculated by taking the variance of the LiDAR measurement time series. However, the dominant radial velocity we get, it doesn't use the full information of the whole Doppler spectrum. It's actually a spatial weighted fluctuation. This spatial weighted fluctuation, we call it filtered radial velocity variance, because this approach will have a damping effect or the filtering effect on the turbulence we get. So this will cause a underestimated turbulence value. And this, so this is a factor that contributes to the systematic error of turbulence estimation using LiDARs. So motivated by the challenge of using nacelle LiDAR to measure turbulence, I raised the first research question. how to accurately estimate turbulence using nacelle-lidars. In this study, we showed the benefit of using a multiple beam LiDAR to measure turbulence. Also, we use another approach to eliminate the probe volume attenuation so that we can reduce the systematic error of turbulence estimation from nacelle-lidar measurement. After the study, we thought even though the spinner LiDAR can be used to accurately measure turbulence, it might be too expensive and too complicated to be widely used in the industry or in general. So we ask ourselves, how do radon stress estimation depend on the LiDAR scanning strategy? I haven't introduced what's radon stress, but I'll come back to that later. So the second paper basically investigates, can we achieve similar performance using a simpler LiDAR? And during the study, actually we found that if the turbulence intensity or the along wind variance is a key parameter or the only parameter that the user care about, because it's the most relevant for load and for power performance, then a single beam LiDAR that is measuring in a steering mode, straightforward, well aligned with the along wind direction is very effective. So we want to use this single beam LiDAR for different applications. The first application we study here is wind turbine control. And here we have the idea to put the single beam LiDAR in the spinner so that it can rotate with the turbine during operations and scans the inflow in the circular pattern, which give us much more information of the inflow compared to just a single beam LiDAR on the nacelle. Also, the benefit is that we can get rid of the blade blockage and have an intended view. The last application is for wake studies. In this study, we use a steering LiDAR on the nacelle to measure the ambient inflow and then study how the ambient turbulence affects the wake mixing. So here, due to the limited amount of time, this presentation will focus on the first 3 studies, and the last study can be found in my thesis. All right, now let's dive into the first study, how to accurately estimate turbulence using nacelle-lidar. The benefit of using a multiple beam LiDAR is that it can give us measurement at different locations among the scanning pattern. This opens up a possibility that we can get a more detailed turbulence parameters from the measurement. And here, the method we use to extract those information is this equation, and it's basically derived follow a least square procedure. I won't dive into the least square procedure, but this equation give us an overview how we can compute those parameters. You can see 6 parameters in the middle of the matrix, in the middle of the equation, and they are variances and covariances of the 3 wind components. U is the along wind component coming from the turbine, V is the lateral component, and W is the vertical component. The 6 parameters, also called 6 Reynolds stresses. And on the left side, we have the M matrix, which is a 6x6 matrix containing the factors containing the elements of the beam unit vector. And on the right side, we have this A matrix, which is a 6x1 matrix containing the beam unit vector and the radial velocity variance. We can see we have 6 unknowns here in this equation, and so we need at least 6 radial velocity variances measured at different locations to fully solve this equation. Therefore, we have this requirement for the LiDAR scanning pattern. The nacelle LiDAR should have at least 6 beams and at least 2 different half-cone opening angles, so that the 6 equations here won't be linearly dependent on each other. We test our method using both LiDAR simulations and measurements from field campaign. And for the LiDAR simulation here, I'm showing a simulation scenario for the 4-beam LiDAR. we can see there is a turbulence box generated from a three-dimensional turbulence model. The color here represents the fluctuation of the along wind velocity. Here we have this dashed circle. This is a wind turbine rotor. In the middle, we have our nacelle-lidar, and this four dot kind of gets hidden in the box is the LiDAR focus point. This turbulence field assumes frozen turbulence, which means that while the whole box passing through the wind turbine, the wind fluctuations in the box doesn't change. To compare with what we see from the simulation, we also analyzed some nacelle-lidar measurements. Specifically, the measurements come from the spinner LiDAR. The field campaign was conducted here, where I will introduce a bit more. And it was on a V52, Vestas V52 wind turbine. The field campaign setup can be seen here in this video. The turbine running in this video is the Vestas V52 wind turbine, which has a rotor diameter of 52 meters and a hub height of 44 meters. Yeah, maybe you have seen this wind turbine and the test site on your way today to the research campus. If you haven't seen it, here the turbine is standing 200 to 300 meters away from the fjord. There is also a mast standing closer to the fjord, and the distance between the mast and the turbine is around 120 meters. The mast is equipped with a wind vane and cup and sonic anemometers at 5 different heights above the ground. It's important to note that we have a sonic anemometer exactly at the hub height of the wind turbine. During the winter 2020 and the summer 2021, there are 3 wind Doppler LiDARs on the top of the wind turbine. As the video plays, we can see them closely. You can see the spinner LiDAR on the top, which looks a bit heavier than the other 2 LiDARs. And there's a 4-beam LiDAR in the middle and the 2-beam LiDAR at the bottom. They are measuring at the same time, more or less the same area. Here, we will mainly talk about, or we only focus the measurement from the spinner LiDAR. To eliminate the probe volume attenuation, we analyze the spinner LiDAR spectrum to get this so-called unfiltered radial velocity variance. Here, I'm showing the instantaneous Doppler spectrum from the central beam of the spinner LiDAR within a 10-minute period. Again, on the horizontal axis, we have the radial velocities, and the vertical axis shows the signal strength. We can see some wind signals in the middle of this plot, and we also see some contaminations with high peaks at a very low radial velocity range. And this is caused most probably due to the blockage of the running blade. So we have to get rid of those contaminations to leave only the wind signals for our analysis. And this is shown in the middle panel. This is the clean Doppler spectrum. Then we average the normalized spectrum to get the resemble average spectrum, which is shown in this blue curve. And we also use the sonic anemometers at half height and project it on the beam direction and plot its distribution, which is shown in the dots here. And these 2 curves match well, matches pretty well. And we use the width of the resemble average Doppler spectrum as the unfiltered radial velocity variance, so that we consider the whole shape of this resemble average spectrum. Here is a comparison of the filtered and unfiltered variances. On the vertical axis, you have the filtered variance, which is attenuated, and on the horizontal axis, we have the unfiltered variance that is using the method before, and each dot here represents a 10-minute period. So we can see from this regression plot that the radial velocity variance has recovered 10% using the unfiltered value compared to the filtered value. Here, our LiDAR was focusing on the 62 meters, so the full width half maximum of our probe volume is around 5 meters. If we increase our focus distance, we might have a larger probe volume, and then the difference between the filtered and unfiltered variance could be larger. We use the method, the equations we introduced before, and the unfiltered variance to compute the radial stresses from the spinner LiDAR measurements, both the virtual measurements from simulation and the real measurements from the campaign. Here, I'm showing you two bar plots. On the horizontal axis, I'm showing the term of the 6 radial stresses. We have first the UVW variances and then the 3 covariances. On the vertical axis, I'm showing the estimation of the radial stresses. The plot on the left is from simulations and on the right is from measurements. The value for the measurements is normalized by the square of the mean wind, to which the radial stresses is mostly proportional. You can see the black line represents the sonic statistics, which we use as a reference. The sonic does measure the wind as one point, just at certain locations. And the spinner LiDAR, we use all the measurements among the scanning pattern. The dots in the plot means the mean value of the statistics from different time periods, and the error bar shows one standard deviation, indicating the uncertainty of our estimation. We can see that for the U variance, the spinner LiDAR performs very similarly as the sonic anemometer, which is very nice. But for the transverse components, the spinner LiDAR, although shows a good bias, the uncertainties are larger. But overall, I would say the spinner LiDAR performs quite well, and it can accurately estimate the 6 radial stress. From the measurements, we can see a very similar trend, although the bias and the uncertainty is different from what we see from the simulation. This is because in the simulation, all the targeted variance in different time periods are exactly the same. But for the measurements, we didn't filter out based on the stability conditions or day and night. So the target variance, it varies based on when you measure. But overall, I would say from the measurements, we see a very similar trend as the left plot from the simulation, and it validated what we see from the simulation. So to summarize the first work, the conclusion we got is following the method, we can use spinner LiDAR in principle to estimate the 6 radial stresses as accurately as the sonic anemometer. At least we see it from the simulations. This means that we can provide to the LiDAR user a more accurate and more detailed turbulence information, which benefits some wind energy applications, such as to assess the power and load and study the wake meandering. Also, it means we can use it in meteorology to study the vertical wind shear, and etc. There are several applications that you can use this estimated radial stresses for. Of course, this work has some limitations. Our methodology assumes that the inflow has homogeneous turbulence. So for inhomogeneous turbulence field, we need to investigate some other methodologies, for example, using least square simulation, constraint simulation, and etc. Now let's go to the second study. We have seen the spinner LiDAR perform so well. What about the other LiDAR, which has a simpler scanning pattern? In this second study, we also used the LiDAR simulations and field measurements, just like the first study. Here, we consider more scanning patterns, more LiDARs. We have our staring LiDAR with 1 beam. We have 2, 4, 5 beam LiDAR, and the 6 beam LiDAR has 5 beams forming a scanning core, and we have a central beam. We have a 50 beam LiDAR doing a circular scan, and we have a 51 beam LiDAR also have a central beam in the middle, and finally our spinner LiDAR. The dashed line is the wind turbine rotor, which covers an area with a diameter of 42 meters. Exactly, we are simulating the wind turbines of 352 wind turbines. Here we are reusing the spinner LiDAR measurement from the same campaign, but we selected the radial velocity measurement at certain locations to mimic the real LiDAR that we considered in our simulation. As we've seen from the first study, to estimate the 6 Reynolds stresses accurately, we need at least 6 beams and 2 different opening angles. So I will first show the Reynolds stresses estimation from these 4 LiDARs in this red square. And here are the results. The characteristic of these 2 bar plots are exactly the same as the bar plot we've seen before. And we have the sonic anemometers in red as reference, a spinner LiDAR measurement, spinner LiDAR measurement represented in black, and 6 beam LiDAR in blue, 50 beam LiDAR in green, and a 51 beam LiDAR in the gray color. Yeah, from the first side, we would see that the green curve, like the 50 beam LiDAR, is not doing great because it cannot fully solve the 6 equations. That's because the opening angle of all the beams are identical, and some of the equations are linearly dependent. Comparing the 50 beam and 51 beam, these 2 lines, we can see the benefit of adding a central beam because it provides a second opening angle. The 6 beam LiDAR in blue, it performs very similarly to the 51 beam LiDAR, although it has fewer beams. And overall, we would say the spinner LiDAR give us the best results, no matter it's the bias or the uncertainty among all the 4 LiDARs. And the spinner LiDAR results we see here is exactly the same as we've seen in the last bar plot. Next, we study the impact of the opening angle. We continue with this 6 beam LiDAR, and this is a 3-dimensional plot showing the trajectory of where the LiDAR measures. The 6 beam LiDAR, we try with 15 degrees half-cone opening angle up to 45 degree half-cone opening angle. From the measurements, since the spinner LiDAR, the maximum opening angle is 30 degrees. So we try from 12 degrees to up to 30 degrees. Let's see the results. We still have sonic anemometer and the spinner LiDAR here as for comparison. And we can see a clear trend that opening up the core angle, we can improve the bias and the uncertainty of the transverse Reynolds stresses, but it doesn't have large impact on the estimation of the U variance. And yeah, we also see the similar trend from the measurement, and it's worth to note that with an opening angle of 45 degrees, although we have only 6 beams, the 6 beam LiDAR even outperforms the spinner LiDAR and have a have a smaller uncertainty. We see the similar trend in the measurement, but we cannot go up to 45 degrees. But the plots are quite similar. When the LiDAR doesn't fulfill this scanning configuration, the requirement for the scanning configuration, but we are only interested for the U variance because we want to assess the load or the power, then we can use some assumption to reduce the number of unknowns in those 6 equations. Here we have three different assumptions. The first one, we neglect other Reynolds stresses components, assume that they are zero, and only care about the U variance. The second assumption, we assume turbulence is isotropic, which means the three variances of UVW components, they are the same, and the covariance are zero, meaning the three wind components are uncorrelated. The third assumption, we assume that the relations between the three velocity variances has this relation as recommended in the IC standard, and the covariances are zero. We apply these three assumptions to all the LiDARs we considered, both in the simulation and using the measurements. We see the first assumption is shown in the solid lines. The second one is the isotropic turbulence assumption in dashed lines, and the IC standard assumption in dotted lines. We can see a general trend from both the simulation and the measurement that the first assumption tend to overestimate the along wind variance. The second assumption tends to underestimate the along wind variance, and the IC standard assumption give us the most accurate along wind variance estimations. This is seems to be the fairest procedure to follow because the relations between the three velocity variances assumed suggested in the IC standard is closest to what we can observe in the atmospheric surface layer among these three assumptions. Now let's summarize the second study about the LiDAR scanning pattern. We have seen from comparing the 50 beam and 51 beam the benefit of adding a central beam. It's good for Reynolds stress estimation. Also, we see the 6 beam LiDAR scanning with a large opening angle gives the best 6 Reynolds stress estimation, and is the best way to scan the inflow for turbulence estimation. Lastly, we saw that all considered LiDARs can measure the along wind variance well using this IC standard assumption, as well as a sonic anemometer. So this work provides some insights and guidance on the designing and utilizing LiDARs for turbulence characterization. Of course, this work has its own limitation because we didn't do a lot of sensitivity analysis on the turbulence conditions or the time intervals. Also, the best LiDAR scanning strategy depends on the user applications, which means how much you value the other Reynolds stresses components except the U variance. Okay, now let's move on to the application part. Can a spinner-based single beam LiDAR be used for control? In the above rated operations, the wind turbine has reached its rated power, and the rotor speed is rotating at a rated value. So the control goal here is we want to maintain the rated rotor speed and at the same time reduce the structural load while the wind, the incoming wind is changing. The conventional wind turbine controller is a feedback controller, which means that it takes control actions after the aerodynamic impact has occurred on the wind turbine structure, so it's a bit delayed. The nacelle-lidar can provide a wind preview, so it's like an eye opening for the wind turbine. It can see the wind before it hits the rotor. The so-called feed-forward controller can use this wind preview information provided by the LiDAR, and if we combine the feedback and feed-forward controller, we can help the wind turbine to react in advance. In order to have a good control performance regarding the rotor speed regulation and load reductions, we need to have a good wind preview. And wind preview quality is evaluated by the rotor effective wind speed coherence, which means how correlated is your LiDAR measured wind preview to the rotor effective wind speed that is really experienced by the rotor itself. The coherence is a value between 1 and 0, and when it drops at 0.5, we define a factor, a parameter called measurement coherence bandwidth. This curve is impacted by the LiDAR scanning pattern. So if we use a different LiDAR scanning pattern, we might have a different curve, and thus we have a different K0.5 value. The higher the measurement coherence bandwidth K05 is, the better is the wind preview. So we use this criterion to optimize first the scanning configuration of our single beam LiDAR based in the spinner. Here we change the measurement range and the opening angle of the beam. Here you can see this is also a three-dimensional trajectory plot, and the red dot is where the LiDAR measures. This is the LiDAR measurement plane, and the blue curve is the wind turbine rotor plane. We consider the temporal evolution of turbulence between the LiDAR measurement plane and the rotor plane. So we calculate the coherence, the K0.5, for different combination of the opening angle and the measurement range. Then we use this optimized LiDAR in our aeroelastic simulation. In this case, we use the tool OpenFast to simulate how the turbine reacts. Here we also use a four-dimensional synthetic turbulence field, considering the temporal evolution, also generated by the turbulence model, and we simulate the turbine reactions to evaluate the control performance using this optimized single beam LiDAR in the spinner. Our reference wind turbine here is IEA 15 megawatt wind turbine, which has a rotor diameter of 240 meters and a hub height of 150 meters. In our simulations, we assume a monopile case, so the bottom is fixed, and we assume there's no wave impact. Here I'm showing the optimization of a continuous wave LiDAR configuration. In this plot, the horizontal axis is the different LiDAR measurement range. Each curve represents a different half-cone opening angle from 15 degrees to 30 degrees. The vertical axis is the measurement coherence bandwidth, K0.5. So each point here represents a combination of a different opening angle and a measurement range. We can see each curve at first increases and then decreases over the measurement range, and we can find an optimum value here. We selected the optimum value to be 21-degree half-cone opening angle and measurement range at 190 meters. This seems not to be the highest point of all the combinations or possibilities here. The highest point is actually at 24 meters with a larger opening angle and a closer range. However, this configuration is not useful or applicable in our case because the LiDAR measures too close to the rotor. So the controller doesn't have enough time to react to the wind disturbance. With the selected optimum point, the spinner-based single beam LiDAR can achieve around 14 times 10 to the power of -3 per second, the measurement coherence bandwidth. And using the same LiDAR on the nacelle, we can only achieve around 1/3 of this value. So it means that the wind preview quality is really improved by putting the same LiDAR in the spinner instead of nacelle. This optimum configuration results in a LiDAR scanning pattern like this. Since the rotor shaft has a tilt angle, so the whole LiDAR scanning pattern is also shifted a bit upwards. Yeah, yeah. The black curve is the our rotor phase, so we can see how much portion this LiDAR scanning area covers. Then we run some area elastic simulations in OpenFast. We have our wind turbine model. We first do some simulation without LiDAR assist control. So we use just the conventional feedback controller. The feedback controller takes the real-time rotational speed of the wind turbine and compare with the desired value, which is the rated rotational speed. It computes the difference and then generates some control demand to tell the actuator how much pitch angle the wind turbine should pitch in order to react to the wind. But it's on the feedback controller, it takes the rotational speed at the last timestamp, so it's a bit delayed. And then we do some simulation with LiDAR assisted control on. So we have our feedback controller, which uses the wind preview provided by our LiDAR. Here we have a LiDAR simulator embedded in the OpenFast. The feed-forward controller can use the wind preview and generate an additional pitch rate to the feedback controller so that it can help the feedback controller to react in advance. Here we simulate the scenario with feed-forward control and two different LiDARs. First is the spinner-based single-beam LiDAR. And we also simulate with the nacelle-based single-beam LiDAR just to compare how much benefit. So here I'm showing the feed-forward control performance. First, let's see the reduction of rotor speed standard deviation, indicating how well the feed-forward control regulates the rotor speed oscillation. So the benefit is compared to the only using feedback controller. So using the LiDAR assist control, we can gain around 13% using this nacelle-based one-beam LiDAR staring in scanning in a staring mode. And this reduction has increased to 47% using the same LiDAR in spinner. And we also simulate a nacelle-based four-beam LiDAR. The scanning pattern is shown in this little plot, just to compare the control performance. And we see that using a one-beam LiDAR in the spinner, we achieve similar control benefits as the four-beam LiDAR on the nacelle. We also look at the damage equivalent load of the tower-based moment in the 4F direction, and we see that using a nacelle LiDAR, one-beam LiDAR, we can achieve just 1%, and this reduction has increased to 4.3% using the same LiDAR in the spinner, which is also on the similar level as what the four-beam nacelle LiDAR could provide. To summary, the third study, we see that the optimized single-beam LiDAR in the spinner can provide a much better wind preview compared to the same LiDAR on the nacelle. So consequently, the control benefit using the optimized spinner-based LiDAR is also much higher than using the nacelle-based option. And the control benefit provided by the spinner-based LiDAR is on a similar level as the four-beam nacelle LiDAR. This work has demonstrated the potential of a simple, robust single-beam LiDAR for wind turbine control, which could eventually reduce the levelized cost of energy. The limitation of this work is in our simulation, we just consider a single wind speed, but the full wind speed range could be simulated to better evaluate the control benefits. Also, we only consider a single measurement plane, both for spinner-based LiDAR and this 4-beam nacelle-lidar. If we consider multi-measurement plane, we could better, we could improve our wind preview quality. We could also optimize the feedback controller in our simulation to gain more load reduction. Here, the feedback controller, we just use a default parameter and we didn't do any optimization for it. So there's still space for the control benefit to improve. Okay, now I would like to give you some take-home messages after this long presentation. First of all, we see from the first study that following a least square procedure, nacelle-lidars with at least 6 beams and 2 different opening angles can estimate the 6 Reynolds stresses accurately. But if we only care about the U velocity variance and the 6 equations cannot be fully solved because we have limited number of beams, then we could use a assumption, a 6 relations of the variances from the IEC standard to reduce the number of unknowns and just to estimate the along wind variance. So we saw in this case, all considered nacelle-lidar can estimate well the along wind variance. We also saw that a 6-beam LiDAR with large opening angle is the best way to measure the inflow for turbulence characterization. The good thing about this 6-beam LiDAR is that it always has a central beam pointing in the along wind direction. So if you open up your half-cone opening angle, you get a better view of the lateral and vertical, so the transverse wind component, and you also guarantee that you always have a good view of the along wind component. So it doesn't sacrifice the estimation of the along wind variance. And lastly, we have seen that a single beam LiDAR in the spinner brings much more control benefit in terms of the rotor speed regulation and the load reduction as a 4-beam LiDAR on the nacelle. So for future work, I would say the most relevant one is our methodology. Assumes that the turbulence is homogeneous. So we need to investigate methods to characterize inhomogeneous turbulence, which is getting more and more important for the turbines with large rotor span or those operating inside wakes or in complex terrain. Further numerical and experimental studies are needed to test the best LiDAR scanning strategy for different user applications. Just like I said, which parameter is most important for you. So it also depends, the LiDAR scanning pattern also depends on how large your turbine is. Thirdly, the field measurements are valuable to test the performance of the spinner-based single beam LiDAR and demonstrate the control benefits. Lastly, more than one single beam LiDAR in the spinner could be used to improve the system redundancy in case the LiDAR is not working, one of them is not working, and to achieve a multi-plane measurement, which could improve our wind preview quality. Spinner-based LiDAR could also work together with a nacelle-based LiDAR. So one steering beam in the middle and a circular pattern, and they could combine together, which also benefits turbulence characterization. So at this point, I would like to say thank you. This project is part of the LIFE project and is funded by the European Union. I would like to thank everyone from LIFE. I know many of you might be online. I'm grateful to have you because we really had a great time together. Also, I would like to thank my supervisors, Alfredo and Jakob at DTU. And I would like to thank Charlotte for bringing us together in the LIFE project. And also, I'd like to thank other colleagues and my co-author, Alessandro in MES. I had a very great time in my 2 secondments in Flensburg University of Applied Sciences with Also my co-supervisor, David, and my co-author, Feng. And I spent a great time at Renewable Energy System in Glasgow, at UK. So thank you, Tom, and the colleagues from RES. Yeah, that's all from my side. Thanks a lot for your attention.